So the first speaker is Zhang, and he will talk about the quantum Oppenheimer-Snyder and Swiss-cheese model. So please.
Okay, so thank you for the introduction, and thank you for the organizers of this conference to give me this opportunity to introduce my work today here. And today I'm going to introduce my work on the quantum Oppenheimer-Snyder and the Swiss cheese model, and also some other related works. And those works are in collaboration with Yuri Klevanovsky, Yunger Ma, Jinsong, Muxin, and Dongxue, based on those works. So the black holes of nature are the most perfect microscopic object. They are in the universe, according to Chandrasekhar. And this picture, this is an artist picture, shows a black hole and some of its interesting features like singularity, horizon, and photosphere, and so on. And also, due to the development of the observational technique in the recent years, so black hole have been observed in our universe, and this is the picture of the image of a black hole at the core of M87 by the Event Horizon Telescope. And this figure shows the gravitational wave produced by merge of two black holes. So as shown in this Penrose diagram of the Schwarzschild black hole, we can see there is a singularity inside the horizon. And the singularity is where the classical GR become invalid. So the existence of singularities in black holes motivate us to introduce quantum gravity to the study of black hole physics. And the loop quantum gravity as a background independent quantum gravity has been introduced in our study on the black hole. However, our answers on quantum black hole haven't formed a unique picture. There are, for instance, those early work by Ashtika Bayova, and also there are the spin-form quantum black hole models, and also different loop quantum symmetry reduced model by different people in our community. So this, so in this loop quantum symmetry reduced model, so that all of the models can be classified into two classes. So in the first class are those homogeneous models. So we just consider the space-time region inside the horizon, and then we consider the Schwarzschild metric, so that the special slice with t equals to constant is of topology R cross S2 and the symmetry T cross S2. And this is a general metric in this coordinate adapt to this symmetry with this variable PB and PC. And by quantization, we mean to promote this PB and PC to operators acting on a Hilbert space. And this is actually what we are doing in loop quantum black hole model. And the second class contains those spherical symmetric model. So in this model, people just consider another coordinate such that the special slice with t equals to constant pass through this horizon. And the special slice also have topology R cross S2, but the symmetry of this model becomes SO3 rather than this T cross SO3. So this is a general metric adapt to this symmetry here. EB and EC, they are just field on R. And again, so quantization is just to promote this coefficient, the coefficient of this metric, I mean EB and EC, to operators acting on Hilbert space. And this is actually a general quantization procedure. And what do we mean by loop quantization? So by loop quantization, what we are doing is just to choose this polymer Hilbert space as the Hilbert space where those operators act on. And by polymer Hilbert space, it is actually a Hilbert space introduced in the standard loop quantum cosmological model. So I'm not going to introduce that much about this quantum theory here, but I would like to show some result. So there is this result based on the study of the on the effective dynamics, like the singularity resolution with different quantum extensions of the Schwarzschild spacetime. And then one can just go to, for instance, those papers to see different quantum extensions to the spacetime. And also the quantum dynamics of those models are also studied by people in our community, including us. And in one of our papers, so we studied the quantum dynamics of the homogeneous model and found that the mass spectrum of the black hole is discrete and has non-vanishing minimal value. As a consequence of this result, so we can just think about black hole evaporation. So that means the black hole, at the end of the black hole evaporation, there may exist a stable remnant. And okay, so here I want to mention like one can go to some other paper by the Spanish group, and they actually get a different result because they use different procedure to solve this constraint. And also in another work of ours, we just studied the quantum dynamics of this spherical symmetric model and found that the usually used effective dynamics is only valid for large black hole. And by this usually used effective dynamics, I mean this dynamics with the regularization of the Hamiltonian such that you just replace this extrinsic curvature by the sine function of this extrinsic curvature, this simple one. And then if we combine this result with the procedure of black hole evaporation, we will find that there should be some phase transition during the black hole evaporation when the black hole mass decreases from a large one to a small one. So we have such exciting result, and however, most of the models don't consider the formation of black hole. And in our universe, so one procedure to form a black hole is to consider the collapse of a dust ball. So we are interested in this topic. What is a black hole space-time containing a collapsing matter ball like? So to answer this question, so we go to the so-called Oppenheimer-Snyder, we go to the so-called Oppenheimer-Snyder model. And this picture depicts the classical Oppenheimer-Snyder model. In this model, there is a homogeneous and pressureless dust. And this dust collapses due to its self-gravity. So according to this classical GR, so the dust ball will not stop its collapse until the formation of a singularity. This is a singularity. And then the matrix outside the dust ball is the Schwarzschild one. So there will be some effect. I want to see here, which will be useful for our further investigation. The first is that, so the dust ball takes this metric, the same as the cosmological one. There is this scale factor A of tau here, and then the dynamics of the A of tau is governed by the Friedmann equation and also the conservation equation. And an important point here is that the Schwarzschild metric outside the dust ball is the unique spherical symmetric and the stationary metric that can be glued to the dust ball metric by the junction condition. Actually, this is a result without necessary to introduce the dynamics outside. That means like if you consider the junction condition, and assume that the outside is spherical symmetric and stationary, so you will get the Schwarzschild one. The point is like here, this classical Friedmann equation is involved in this model, and the question we want to ask is like, what will happen if we replace the dust ball by a loop quantum cosmological dust ball? So that means like we still consider this collapsing dust ball, and inside this dust ball, the metric takes this cosmological one. However, here the scale factor A of tau is governed by this modified Friedmann equation proposed by loop quantum cosmology rather than the classical one. Of course, we still need this conservation equation. And then we just assume that the metric outside the dust ball is like a spherical symmetric and stationary. And so that means like this metric takes this general form with respect to some function f of r and g of r. And the question we want to answer is like, what is the expression of this f of r and the g of r so that the outside can be glued with the inside by this junction condition. Sorry. Okay, and this question is answered by our paper published last year, and by our calculation we found that this metric actually takes this form, and with this function these functions take this form, and with those function f of r and g of r, we can see actually the metric is just the quantum modified Schwarzschild one with the quantum modification term proportional to this 1 over r² power 4. So this is the result, and there are some remarks I want to emphasize here. The first is that the outside metric is uniquely determined by the modified Friedmann equation. So for instance, if we consider so here this h is the Hubble parameter. Sorry. So if we consider this modified Friedmann equation involve a general function x of rho here, we could get this f of r and the g of r just take this form which related to this function r. And also another point is that the same metric is also obtained by other people in our community from various approach. Actually, from our knowledge, this metric was first obtained by Arthur and his collaborator in 2015, and then rediscovered by different groups of people in our community from different approaches. And also in our work, we studied the Penrose diagram of the maximal extended spacetime of this metric, and the result is shown here. And the Penrose diagrams are very similar to that of the Rn black hole. There are those 3 cases, and there is this parameter minimum mass for the dust ball with mass smaller than this minimum mass. There is no black hole, and the black hole exists only for the dust ball whose mass is equal to or greater than this minimum mass. And here this dashed red line is actually the word line of the sphere of the collapsing dust ball in this spacetime. Okay, and the point is like in our model, we also have this black hole to white hole transition. Like from here, there is this black hole, and here it is a white hole. However, in comparison with other models like this APS model, I would like to see. So in this model, we actually have a transition region, like this shadow region here, rather than a transition surface. And with this is actually our work, and with this metric, a question we want to ask is like if there are any observational effect on this quantum modified spacetime. So in order to answer this question, so we just consider the following scenario. So assume that we are the observer standing in this universe A, and then in this universe A there is this black hole B we assume that there is a accretion disk surrounding this black hole B, and there are those radiation emitted from this accretion disk. And then those radiation will reach the observer at infinity and give the observer some black hole image. And we want to ask, if there is any deformation on the black hole image due to the quantum correction term, and we do our calculation and show in our paper, the answer is yes, there are some deformation. However, those deformation as shown here, it is actually very small. And this is not a surprising result because here we only consider the physical procedure happens outside the black hole horizon. And as we know, for a large black hole, the region outside the black hole horizon is actually can be well described by the classical GR. So because of this, we can imagine, so in this very semi-classical region, if you consider such quantum effect, it must be very small because our theory has a correct semi-classical limit. And the quantum correction to this, the quantum correction term becomes significant actually nearby the singularity. And this quantum correction extends the Schwarzschild space-time beyond the singularity. So the point is that in order to get some significant observational effect, we should use this quantum extension. And then in another work of ours, we just study another scenario. So again, this observer, so our friend Lewandowski, still in this universe A, and then, however, because of the quantum extension, so there is in the past of this universe A, there is this universe A prime, and in this universe A prime, there is also a black hole B prime. And we just assume that there is also an accretion disk surrounding this black hole B prime, and there are those radiation coming from this accretion disk and entering the black hole B prime. By our calculation, we found that those radiation entering the black hole B prime will pass through this highly quantum region and show up in the universe A from this white hole horizon. And because this radiation actually pass through this highly quantum region, so they should carry some information about this quantum correction to the space-time. And then we want to ask, so what will be the black hole, what will be the image produced by those radiation coming from the universe A prime? And this is the result. This picture, the left one, is the image given by those radiation coming from the universe A prime, and this is the initial one. I mean, this is the image given by those radiation in this universe A. So like what we observed, and this is the superposition of this two one. And we can say, due to those radiation coming from the universe A prime, so there will be those extra light rays in this shadow region of the original of the initial black hole image. Actually, one can just go to measure the position and the width of those light rays, and then we can get actually the detailed information about the quantum correction, to this Schwarzschild space-time. And this is, I would like to say, this is a very nice result, and it opens a new window to observe the quantum correction to the Schwarzschild space-time. And one can also go to those papers for the similar application to regular black holes. However, however, it is not without debate. The point here is the existence of a Cauchy horizon, and by those work, so it is found that the existence of the Cauchy horizon may imply that the space-time is actually unstable under perturbation. If that is the case, and we just consider the back reaction of those radiation from this A prime to this space-time, and the whole space-time structure could be completely destroyed by those back reaction. And then if that is the case, so that means like our previous prediction could be unreliable. So because of this consideration, so we just move to another new model proposed by Mushin, Carlo, and Fashit. The point here is to consider the quantum gravity effect at the end of the black hole evaporation, and then this quantum gravity effect will change the global structure of the space-time from here to here. I'm not going to introduce that much about this modification, and I think Fashit this afternoon will tell more details about this modification. But here I want to see some point in this new space-time. The first is that the metric is locally the same as ours, except for this B region in this new space-time. And the second is like in this space-time, there is actually no Cauchy horizon, so it could be stable. It could be stable. And since the metric in this new space-time is the same as ours, we can just combine our previous result and this new model. So assume there is this accretion disk here emitting radiation. And this is the word line of an observer far away from the black hole. And then some of the radiation will move away from the black hole and be accepted by this observer at the space-time point alpha. And then the observer will get the black hole image looks like this. And then some other radiation will also enter this black hole, and just use our previous calculation, and those radiation will enter the black hole and finally reach the observer at the space-time point beta. Space-time point beta in the future of this alpha, and by our previous calculation, so it will be like an image looks like this. And based on this argument, let us assume that we are the observer, and we have a telescope to focus on a black hole far away from us. And if this is the true story, so what we will get? So what we will get is like in our telescope, the appearance of the black hole will change as time goes by. So it is just like a movie. So if you use the telescope to observe this black hole, you can see a movie on the evolution of the appearance of a black hole in our telescope. Okay, and this is like an interesting story, and the question here is like, what is the dynamics in this B region, in this new space-time? And then we just go to this topic, and according to Carlos' lecture this time, so the dynamics in this B region should be governed by the spin-form model. And as what we know for the spin-form model, the key quantity in this model is actually the spin-form amplitude. And the spin-form amplitude can be numerically calculated with different algorithms. For instance, if we focus on the small spin regime, so we can use the algorithm introduced in those papers, for instance, as also Pietro's talk yesterday, to do the calculation. And also, if we focus on the large spin regime, so we can use the algorithm, for instance, in this paper called the complex critical quantum method, also introduced by Dongxue yesterday to do the calculation. And in our new work, so we just used the second algorithm, this complex critical method for large spin to study the dynamics of this B region. And the paper has been published online. And I don't have that much time to introduce that much details about this work because it is actually really technical. And I will just introduce some key point and key result about this work. So the first is like in this model, we just locate this boundary of this B region in the semi-classical region of the space-time, so that the boundary state can be chosen as a coherent state labeled by the triad and extrinsic curvature. And the spread of this coherent state is denoted by T. And then due to, because we locate this partial B in this semi-classical region, so we can consider the amplitude as the T goes to 0 because T is the quantum fluctuation. And this limit T goes to 0 is actually equivalent to the limit that spin go to infinity. And this is the reason why we can use this algorithm for large spin regime for our calculation. And the key point in our work is the following. So in loop quantum gravity, this plus and minus E are regarded as different states because we consider only this SU2 gauge transformation. And if you consider this gauge invariant state, actually the coherent state corresponding to plus E and minus E, they are in different gauge orbit, so they are different states. However, as we know, so in this classical geometry, so plus and minus E gives us the same 3D metric QAB. And what we know, actually the boundary, because we put this in a classical space-time, and what we know on the boundary is QAB rather than EAB. And so this fact seems to tell us that the boundary state should be chosen as the superposition of the coherent state with respect to plus and minus E. So in our work, we just choose the coherent state, the boundary coherent states like this, and in this tensor product, the first factor is the state located on the past boundary, and the second factor are the state on the future boundary. And because of this choice of the boundary state, so in our spin form amplitude, there will be 4 terms. And the whole amplitude is a summation of those 4 terms. And we are just going to use the complex critical point method to compute this one by one. And here, in our work, we consider a non-degenerate 2 complex containing 56 vertices. And I just want to use this number to tell you that we actually consider a very complicated complex. And then we found that the first 2 terms in this amplitude dominate this amplitude. And then if we consider the geometric meaning of the first 2 terms, they actually can be interpreted as this transition from plus E minus to plus E plus, or from minus E minus to minus E plus. Here, this subindex minus and this subindex plus means the triad on the past boundary and the triad on the future boundary. And then if you calculate the determinant of this E plus and E minus, you will find this relation. And this result seems to tell us that, so if this black to white hole transition could happen, so it should be accompanied by the quantum tunneling between the opposite orientations. This is the result. This is what we concluded from this fact. And also in our paper, so we also get the value of the effective action in the amplitude at the grid point, and it is looks like this. And I just want to show this result and to tell you we get some number, but actually in our work we haven't do further analysis on the meaning of those two numbers. And this is the choice of the parameter in our calculation, and the code is here. Is here, and this is really a work I like very much, and it is really technical. And if you are interested in it, just do not hesitate to come to me. I would like to tell you more details about this. And this is my talk today, and I would like to use those figures as a summary of my talk. So at first, we consider the Oppenheimer-Snyder model and get a metric with a quantum modification term to the Schwarzschild one. And also we studied the potential observational effect on these quantum corrections. And due to some issues of the unstability of this space-time, so we just go to some new model introduced by Mushinkalo and Fashida, and do some argument by combining our calculation and this new model. And also in our recent work, we also studied the spin-form dynamics of this B region in this new space-time with the complex critical point method. Okay, thank you for your attention.
Thanks for the very nice talk. So, Carol, first question.
Thank you. Very nice. I have a specific question. First, let me say that that metric there that you introduced seems to me by far the best guess we have for approximating the effective metric of what goes on getting into the quantum region of black hole. I'm very excited by that. It seems to be very interesting for me. The question I have, it regards your beautiful sort of prediction of what one would observe in the future from the black hole. That's tempting and exciting, because this is even if it's not concretely visible, that would be something we could think. Quantum gravity tell us how. But the question is the following. I would expect on physical ground that once you fold in the dissipative aspect of that and the Hawking radiation, if you have a big black hole to start with, before the B transition, most of the energy is radiated away, so the white hole that forms is much smaller. And the question is that going to change your, it's going to be destroyed, or you could still run your argument about the prediction of what you said?
Yeah, so I actually thought about that question after your lecture. The answer is like I haven't know. So this is the point. I don't know what is the. So I don't know if we could still get some picture like this.
Yeah.
But what I'm thinking now is like if you consider the black hole evaporation and the white hole becomes very smaller, and I think this procedure I consider should still have, because there should be something coming from the previous universe or something like that. But I just don't know what we can get.
Yeah.
Maybe just this white hole or like a particle becomes some brilliant one or something like that. I actually don't know what it is.
Okay. No, that there is some effect, of course. I mean, I see no reason to lose it. It's just quantitatively how the question was how quantitative would be the effect by the loss of mass.
One thing I would like to say. So if that is the case, and according to my experience, and my experience may not be correct, but I think it's something like that. So there should be, if even that happens, there should be something in this shadow region. I mean, so this
Yes.
like this breath still like, yeah.
Yes.
Maybe it's not like a light rings, but like a light point or something like
Yes.
that. I'm not really sure about that.
Thank you. This is great. Thank you very much.
Further questions, comments? Yeah.
My question is more basic. I mean, in a sense, the Oppenheimer-Snyder dynamics can be seen as a sort of unstable point in this. Yeah, do you hear me? The Oppenheimer-Snyder dynamics, that is, I totally agree, is symmetric around the bounds, can be seen as a sort of unstable point in the space of solutions given by all possible initial data, in the sense that if you go even...
I'm sorry, can we see what? Can you speak a little slowly?
Yeah.
I cannot follow you, sorry.
Yeah.
It's my
I was
English.
saying that if you consider profiles close to Oppenheimer-Snyder but continuous, okay, then you obtain a shell crossing singularities. The only situation in which you don't obtain a shell crossing singularities if you have a profile of compact support, so that does not goes at infinity, as for example in the cosmological case, is in the Oppenheimer-Snyder case. So it's the only profile that does not develop shell crossing singularity, and for which, therefore, the dynamics can be symmetric around the bounds. If you go a bit outside that, you obtain the shell crossing singularities after the bounds, and the dynamics changes completely. I mean, for example, the time symmetry is broken, and also the picture changes, also the Penrose diagram. So my point is not a question, more what you think about that, if makes sense keeping look only at Oppenheimer-Snyder, because it's, in a sense, it's idealistic and is not stable. In a sense, if you perturb a bit that, you obtain something completely different. So yeah, that is what do you think about this?
So to be honest, I actually don't know what is this singularity. You tell like a cross.
Yeah.
Share.
Okay.
Yeah, I'm sorry,
Yeah,
I didn't. I have that much idea about that, and moreover, so in our work, so you can see we actually get this metric by this junction condition. So that means like we assume some metric inside, and ask that this 3D metric and the extrinsic curvature is continue from outside to inside, and then we get this metric. So there is no dynamics in this one, and I think if we want to consider the dynamics, we should go to Edwards model or Hongguang's model, and they introduce the thing. And one thing is like the instability. I don't know if it is related to the instability I introduced here. But I have no idea.
Yeah, the Oppenheimer-Snyder case is special in a sense because I mean you have an infinitely sharp boundary, and that there is no this kind of singularity. Fundamentally, yeah, you have two shells, one that bounces, that is in the core, and the ones in the tail if there is a tail. So if there is a continuous profile that instead is keeping in falling. And fundamentally is that the mechanism that produces the singularities. Clearly, Oppenheimer-Snyder is avoided because all the shells that compose the matter bounce together and move together. And,
Okay.
But yeah, in the general case,
so let me learn something about this and to see if I have any comment to your question. But thank you.
Thanks.
Any other comments, questions? Yeah, if no, let's thanks again.
Okay, thank you.